In this video, we will see 4 examples of first-order separable differential equations. It's straightforward to solve separable equations. Therefore, whenever you have a first-order problem, you might want to think about this approach first. Example 1. In this example, we have 2 terms with the derivative of y. Recall that an equation is so-called separable if its derivative can be written as a product of 2 one-variable functions. So we need to get the y prime isolated first. And in this case, we're going to do some algebra. So we can subtract both sides by 3x y squared y prime, so that you get the 2 y prime terms in one side and the other terms in the other side. And then we can factor the y prime out and then divide both sides by the coefficient. And it is a factored form so that we can check whether or not the factors depends only on one variable. It turns out one of them depends only on x and another one depends only on y. So that means this equation is variable separable. And for separable equations, we can go ahead and separate the x and y parts. In particular, recall that the differential of y is defined as the derivative of y times the differential of x. And now you can put the derivative of y into this expression, and you can try to separate the x and y parts. And in particular, in this case, you need to put the y part into the left-hand side. You just multiply both sides by this function, and then you end with the separated form. And now we can integrate both sides. This right-hand side is pretty easy to integrate. And for the left-hand side, the 3y squared is also straightforward. So for the cosine 2y, we have to use substitution. In particular here, we're going to introduce a new variable u, which is the argument of the cosine, which is 2y. And then you get du is going to be twice of dy, which means dy is half of du. So now you can write everything in terms of the new variable u. And this is going to be an easy to integrate function so that you end with half of sine u. And by the definition of u, you get half of sine 2y with a constant. Now you put the antiderivative of cosine 2y into the equation here. And 4 times of this will give you twice of sine 2y, and then 3y squared will give you the y cubed, and 1 over x will give you natural log of absolute value of x. And because here the x is greater than 0, we know the absolute value of x is going to be the same as x. So we end with the general solution to the equation as this. Here, notice that although when we do the integration on the 2 sides, we got 2 constants here. But these 2 constants actually can be combined into one generic constant. So you don't have to write 2 constants, but 1. Example 2. For this example, the derivative is already isolated. So you just need to check whether or not the right-hand side can be written as a product of 2 one-variable functions. That means you have to factor the right-hand side. And we know for a 4-term polynomial, we can try the grouping approach. For example, like this one, we can group the first 2 terms and group the last 2 terms. For each group, you try to find some common factors. And then you're going to say the left part, they are the same. That means that's another common factor, so that the polynomial can be factored as 2x minus 3 times y minus 2. And both factors depends only on one variable. That means this equation is a separable equation. And we can use a similar approach as we did example 1, namely, we write the differential of y as the derivative times the differential of x. And now you try to separate the x and the y parts. In particular, in this case, you need to move the y minus 2 to the other side. You can just divide both sides. And then you see the separated case. And then you can integrate both sides. Again, the right-hand side is pretty easy to integrate. And for the left-hand side, we can do substitution. And for this case, we can define the u as y minus 2, so that you see the du is going to be dy, and the integration can be written as the integration of 1 over u, and its antiderivative is just natural log of absolute value of u, which is natural log of the absolute value of y minus 2 eventually. And now you put it into the original equation, and you also integrate the right-hand side, so that you end with an equation like this. Once again here, we will have two constants combined into one. Well, for this case, because you have only one y term, so we can do something to figure out the y. In particular, we raise the e to the natural log power so that we can get the y minus 2. And then we can just use the right-hand side to replace the natural log. And then we use some properties of powers. We can get this exponential term can be written as a product of 3 exponential terms. And here, the e to a constant power is going to be still a constant. So we'll just write it as c. Well, in differential equation class, we consider c as a generic constant. Its value is not necessary to be always the same. And another thing we used here is the negative exponent is defined as a reciprocal. Okay, now for this expression, you can go further to remove the absolute value bars. We understand when we do that, you can just change the sign of the expression, but the sign can be absorbed by the constant c. So eventually, we're going to get the y is going to be c times e to the x squared over e to the 3x and then plus 2. You see the 2 here, move to the other side, it's going to be plus 2. So this will be the general solution to the differential equation. Example 3. This example is different from the first two in 2 features. One feature is it's given as a differential form. You don't have the derivative here. And the second feature is we have a point on the solution curve. And this is understood as the initial condition. We're going to explain how do we apply this condition. Well, for a differential form, you can, of course, get the derivative and then use the definition for separable equations. But for this case, because you notice that the coefficients for the differentials, they are factored. And each factor depends only on one variable. So it's pretty obvious we can separate the x and y parts, okay? So this equation actually is separable. Well, to separate the x and y parts, you can say this is the only thing we need to move to the other side because you already have the y's in the left-hand side and you have the other x in the right-hand side, right? So this is the only term you need to move to the right-hand side. And we can easily do that, right, by dividing both sides by x plus 1. And now we're going to integrate both sides. And this time, the left-hand side is easy to integrate. But for the right-hand side, we can do the substitution again. In particular, in this case, as you can see, I'm going to first of all write my original expression as, so you can see the numerator, I'm going to get a plus 1 and a minus 1 in the numerator. So here we didn't change the numerator, but the x plus 1 over the x plus 1 will give you a 1. And then this 1 over the x plus 1 can be handled by using substitution. Well, now for the second term here, we can define the u as x plus 1 so that your du is going to be dx. And the integration can be written as the integration of 1 over u, so that you're going to end with eventually x minus the natural log of x plus 1 absolute value, and then plus a constant. Well, again, this constant can be put, the two constants from the two sides can be combined into one constant, okay? And you put this expression into the original equation, and then you're going to get the general solution is going to be something like this. And in this case, because x is greater than -1, so the absolute value of x plus 1 is the same as x plus 1. So we can write our general solution as y squared is equal to x minus natural log of x plus 1, and then plus a constant c. But if you don't have the initial condition, we're already done. But we do have a condition here to apply. And how do we understand this condition? We know when we talk about point 0, 2, that means the x coordinate is 0 and the y coordinate is 2. So that means when your x value is 0 for this equation, your y value is going to be 2, so that this point is going to be on the curve, means it satisfies this equation. So that means we can just plug the 0 and the 2 into the places of x and the y, and then we end with the equation for the constant c. And for this equation, you will say we're going to get 4 is equal to 0 minus another 0, because this is log 1, which is 0, right? And then plus c. So that means your c is going to be 4. So finally, we can plug the 4 into the place of c in the general solution, and then we get a particular solution to the initial value problem. Example number 4. This one is similar to example 3 because it's also given as a differential form, and also you have an initial condition. Well, we notice that the coefficients for the differentials are once again factored, and each factor depends only on one variable. So therefore, this is a separable case. Actually, you can easily say it is separable, okay? For example, first of all, here we separate the two terms in two sides of the equation. And now we can say dy is supposed to be with the y parts, right? But you have an x function. And the dx is supposed to stay with the x parts, but you have a y function. So you have to move the cosine x and e to the y to the other sides. We can simply divide both sides by cosine x and divide by e to the y, right? And then we can get the separated case like this. Okay, now we can simplify both sides and integrate them. In particular, you can say the e to the 2y divided by e to the y will give you e to the y. And you can write the y over e to the y as y times e to the negative y. And for the right-hand side, the sine 2x, by using the double angle formula, we're going to get twice of sine x cosine x. And then you can see some cancellations here. So we end with some integration form like this. So we just need to integrate each term. You will say the first term is pretty easy to integrate. The sine x is also easy to integrate. So the y times e to the negative y, this one requires some extra effort. And for a product of two types of functions, we can use integration by parts. Well, here is the formula for integration by parts. And to apply this formula, we have to identify a u and a v prime. Usually, if you have the two products with a polynomial involved, just like in this case, you get y times e to the negative y, so y is a polynomial, right? We'll usually let the u to be the polynomial, and the other part
to be the v prime. The reason is, well, when you do the integration by parts formula, you're going to change the original integration problem to a new integration problem with u prime and v. And if you have u is a polynomial, then the u prime is going to be a degree 1 less than the original polynomial. And we understand if you have a polynomial of a less degree, it's considered as an easier problem. And for this particular case, you can say if u is y, then u prime is 1. And the v from the v prime, you can say it's going to be negative e to the negative y. So essentially, the v and v prime, they are the same type of function. Therefore, you can say the new integration problem is much easier. You have only one function left, not a product of two functions anymore. Anyway, by applying the formula, we get the integration of y times e to the negative y is going to be negative y times e to the negative y, and then minus e to the negative y with a constant. Okay, now we're going to just plug this into the equation and be careful of the signs, okay? And then we end with a general solution to the original problem, which is e to the y plus y times e to the negative y, and then plus e to the negative y is equal to twice of cosine x plus c. Well, once again, we have to apply the initial condition to determine the c. And here, the initial condition y of 0 is equal to 0 means when x is 0, your y is 0. So you can just plug the zeros into the places of x and y. And in this case, you're going to say e to the 0 is going to be 1. And here you have another 1. And the midterm, 0 times whatever is 0. So you will say the left-hand side is going to be 2. And for the right-hand side, cosine 0 is 1. So twice of 1 is 2. So you end with 2 is equal to 2 plus c. That means c is 0. Finally, you can plug the c is equal to 0 into the general solution, and then you can find the particular solution to the initial value problem. Well, to summarize, we will say for separable equations, we can just separate the x parts with its differential and the y parts with its differential. And then we can integrate both sides directly. So the difficulty is going to be how to integrate the two functions. Okay, that's all for this video, and thank you for watching.